Hi everyone, and welcome to lecture 11 for Math 350. And this week we're going to be working on recursive functions and techniques for working with them efficiently. So a recursive function is a function that you define in terms of itself. It's an idea that we come across in many places in mathematics, and it's one of the core ideas of computer science. So this lecture may be shorter than some of the previous ones, but it doesn't mean that the problems that are associated with this lecture are easier. In fact, in some ways they're more challenging because working with recursive functions involves thinking about how to structure a problem that you're working on in a way that's amenable to recursion. And so you'll see what I mean by that when you look at the homework exercises, and you can see how exactly it is that where the difficulties come from in thinking about how to take a process that seems recursive and then actually implement it into code. And there's a particularly good problem on the homework exercises this week that I'm really looking forward to working through. So, to begin with, we should think about or remind ourselves of what a recursive function actually is. So a recursive function in mathematics is a function that is defined in terms of its own preceding values. So the first recursive function that most of us learn is the Fibonacci sequence. And you get the next term in the Fibonacci sequence by taking the two previous terms and adding them together. Now, that means that we have to have starting point. So the Fibonacci sequence is the sequence defined where the first two numbers are 1 and 1. So once I have 1 and 1, I can construct the next number by adding those together to get 2. And then I can take 2 and its previous term, 1, and add those together to get 3. And then 3 and 2 is 5, and so on. So if we wanted to do this in Mathematica, we might take the naive approach of just writing it and see if it will do it. So if we write down this function fib, and we're going to set two initial values because this function is going to require some starting place. So if we write down fib of 0 is 1 and fib of 1 is 1, then I've got a function now that I can evaluate in terms of itself. This might look weird, but this is a pretty typical structure in computer programming to define a function in terms of itself. And what it will do when you call it is it will look back at the previous function calls and then evaluate those. And if those have further calls inside of them, it will keep going backwards until it finds something that it knows. So our function definition is that the Fibonacci fib of n is equal to fib of n minus 1 plus fib of n minus 2. So let's test this out. The 1 and the 1 here came from the fact that I did not put my semicolons at the end of the values there. Okay, so let's test it. So if according to my formula, if I put 2 in here, well, that's going to call f of 1 plus f of 0, which is going to be 2, because 1 and 1 is 2. Fib of 3 is 3. That's good, because 2 plus 1 is 3. And I can keep going. I can test various numbers. The Fibonacci of 10 is 89, so on. Now, there's something you might notice. Maybe since we're dealing with small values, you haven't seen this yet. But the problem, not the problem, what you might notice is that as we evaluate larger and larger numbers, this program takes longer and longer to run. So if I put in 35 here, the program is going to take quite a while to produce the 35th Fibonacci number this way. In fact, it's still going. And you might think to yourself, why is it doing that? What is about Fibonacci of 35 that's taking so long for the computer to execute? And yeah, we're just going to sit here and wait for this to finish evaluating because there was a big difference between f of 30 and f of 35. All right, so there is the 35th Fibonacci number. It's correct, but that took 10 seconds to evaluate. So the question is, why did it take that long? The answer is that what Mathematica is doing when it calls fib of 35 is it's evaluating that to be fib of 34 plus fib of 33. So now it's got two things to evaluate. But then each of those has two things to evaluate. And it doesn't know that it's already done some of the information that it needs to compute in one of the branches. So it recomputes everything at every step. So let me see if I can illustrate what I mean by that. Mathematica's process, for example, say for a Fibonacci sequence of 6, for a fib of 6, is to get fib of 5 and fib of 4. So now both fib of 5 and fib of 4 are evaluated. Notice though that fib of 5 is evaluated as the f of 4 plus f of 3. Well, it doesn't use the fact that it already evaluated this Fibonacci function at 4 to calculate this one. It redoes it. And so you get this huge tree of expanding cases where things are being evaluated over and over and over again. And this is not a way that a person would ever think to evaluate this. You would evaluate everything once. So we can actually see what's going on by looking at the tree form. There's a function here called trace that is going to be explained in the memoization notebook that accompanies this week's homework. I'm going to use it here and just tell you that what the trace function does is it looks at how a function is evaluated and it returns every copy of a pattern that you specify. So right now what I'm asking it to do is trace the execution of Fibonacci at the number 6 and then pull out every place where it evaluated a copy of the fib function. And then I'm going to put that into tree form so I can see what the output looks like. And you could see that if you look at the tree form here, there's an enormous number of function calls that have happened. In fact, we can make this larger and you can see that that tree gets significantly more complicated. What you would expect to happen if this was acting in the way that a human did it is that it would know that to get Fibonacci 8, it would have Fibonacci 7 and Fibonacci 6 stored somewhere so that it could just pull those numbers every time it needed to do a new evaluation. So you can avoid that constant reevaluation of Fib 7 and Fib 6 and Fib 5, which if you're, again, in the memoization notebook, you'll see exactly how many times that's being reevaluated. It's completely absurd. So we can use a technique called memoization, which for the purposes of this lecture, you should think of as storing the evaluations that have already happened to make sure that Mathematica can call them back up again when it needs them instead of constantly reevaluating everything every time. So the way we can do that is when we define a recursive function, we can not only tell the function how to look at its previous values, but to actually store that information as well with the correct label. So this might look a little strange, but what this function is doing is it's defining Fibonacci of n to be a function assignment, a variable assignment. It says fib of 8 is equal to the assignment fib 8 is equal to fib 7 plus fib 6. So that means that in the course of calculating what the 8th Fibonacci number is, it also records that number inside of something called fib 8. And now Mathematica will carry that around internally as a value it can refer to again. Because the way that Mathematica acts is it always tries to call the most specific variable name it can find. So if Mathematica sees fib 8, and on the one hand it has a function definition that it can compute fib 8 with, but on the other hand it's stored something called fib 8 in memory, it will just pull the fib 8 from memory and use it instead of recomputing it. So now, it took a long time to compute fib 35. This will be our redefinition of the fib function, and now let's compute it again. Well, that was almost instant. Okay, so, and all of the values between fib 1 and fib 35 are now sitting in memory. Of course, we can check that by looking at the command, what is stored inside of fib? And you can see, this is the trade-off that we've made. We have traded speed for memory. So now Mathematica is carrying around in memory all of these values of the Fibonacci numbers that it can just call on when it needs to. So let's look at some examples of recursion that are not just the Fibonacci sequence. So the first thing is, let's look at an example we've actually computed 2 different ways already, which is a function to produce the sum of 1 over the factorials. And this is called en, of course, because this sequence ends up converging to the number e in the limit. So if we're going to set something up as a recursive operation, then we need a starting point always. And the way I'm going to think about this function is, well, the 0 value is equal to 1, and then I get the next number in the sequence by taking the existing number and then adding 1 over n factorial to it. Okay, so I look at the previous en and I add 1 over n factorial. And that's what I'm saying here. E2 is, E1 is E0 plus 1 over 1 factorial. E2 takes E1, which was this bit right here, and adds 1 over 2 factorial to it. En is going to take En minus 1, which is all this, and is going to add 1 over n factorial to it. So we're going to write En is equal to En minus 1 plus 1 over n factorial. And notice that I've used the same memoization trick here to make sure that this runs efficiently, where my definition of the function is not just a calculation, but it's going to do the calculation and then also store it in a name so it can be recalled when necessary. So you can compute this if you like for large values of e, and so on. E of 300 is a large number. I'll show all of it so you can see it. It's a pretty big number. It's a fraction. So actually, I'm curious here what this is equal to. Oh, that's starting to get pretty close to e at this point. So one thing to notice about, one thing that you might run into when you're working recursively is that Mathematica actually has an internal limit on how many recursive steps it will take before it quits. So if you tried to evaluate this command at E3000, it's going to tell you that it's hit its recursion depth, which means that it will not run this more than 1024 times. And it does that as a hard barrier against out of control processes, which are easy to do when you're doing recursion. If you want to go further, then you can redefine the recursive limit to whatever you want it to be. So the appropriate response to something like this would be to redefine what's called the global variable in the following way. So any global variable in Mathematica can be set with a command that looks like this. So we're going to take the recursion limit variable and we'll reset it to say, I don't know, 6,000. Now, having done that, we should be able to run this command again, and now it will produce our number for us because at this point, it'll recurse 6,000 times instead of the 1,024 times that it's set by default. So just an option that you should be aware of when you're looking at these things. A thing to keep in mind is that when you're approaching a problem recursively, that oftentimes that's a mathematically elegant way of thinking about how a problem works. The issue is that computing recursively tends to be more expensive than computing directly, at least the first time through. Once you have built out a bunch of cases using a recursive function and you've stored those values, it's very easy to refer to them again. And so there's a trade-off here between an explicit function that can always just compute a value based on an input and a recursive definition of a function that is very fast once it's computed all the values once, but is a little bit slower if you're computing a value for the first time. And I want to illustrate that. If we define a new version of the function e with this 1 plus the plus applied to 1 over the range of n factorial, that's the same function, but from a list-based approach where we take the range 1 to n, we factorial it, we take 1 over that, and then add all those together. That's an explicit way of computing this function en. So if we do that, and we hit it with this absolute timing function, and absolute timing gives you an output that the first entry is how long the function took to execute, and the second entry is the output of the function. If we do the absolute timing of this function running once on an input of 1,000, we see that we've got 0.004 of a second. Okay, so 4,000th of a second is about how long that explicit function took to run. Now I've cleared the definition of e so that I can feed it back in again. And the reason I did that was so that I don't have the values pre-stored, because I want to compare how long it took to run the first time to the second time. The first time that we run our function with an input of 1,000, you can see that this has taken 10 times longer to run on the first go. So this is 400ths of a second that our function took to run versus 4,000ths of a second. And that difference is going to get even more pronounced as the input gets larger and larger. However, the second time we run it, it has all those values pre-stored in memory. So the second time through, it takes a millionth of a second to produce a number, as opposed to the 4,000th of a second that we've got right here. So there's timing issues to think about when you're working with recursive formulas versus explicit formulas, and also the trade-off between running a recursive formula once and getting a table of values that you can refer back to, in which case that function is going to be very fast if you're having to use it over and over again. So the big trade-off that you're making when you're using recursion and you're memoizing is that you're trading speed for memory. So we're having to store things in memory to make them fast. This used to be a way bigger concern in the days when computers had very, very strict limits on the amount of memory they had available. Now, basically, you can think of memory and storage as free. Computers have enormous amounts of RAM and enormous amounts of hard drive space. And so it's very easy in most cases that you're going to deal with as a mathematician to trade speed for memory in a way that's not really going to cost you anything, because we have so much free space available in memory. So right now what's happening is this function e is holding 1,000 values of e in memory as a table, but it doesn't hurt anything because, I don't know, my computer has 24 gigabytes of RAM inside of it, right? And way more hard drive space than that. So another interesting place that you can use recursion that shows up frequently in applied mathematics is in the generation of special families of functions. And recursion is an equally good way of looking at the generation of functions as well. So one of the most important families, I've picked one. There's 6 or 7 of these that show up in sort of introduction to differential equations and linear analysis, is the Legendre polynomials. So Legendre polynomials are one of the central sets of polynomials that show up in applied math. So you can use them for approximation theory, for example, and they show up in a lot of applications of physical systems as well. They are one of the ways to define the Legendre polynomials is as the output of a recursive relation, where you start with the first Legendre polynomial being equal to 1, and the second Legendre polynomial being equal to x. And for n greater than or equal to 2, you have a formula that looks like this that defines all of the rest of them. Okay. Now, we want to write a function that generates Pn, but not just that generates Pn. We want it to generate P and is still a function of x. That is, we want to be able to work with it as a function. We want to be able to plot it, to do numerics to it. We might want to integrate it. We have to multiply it by other functions. So I need to make sure that it remains a function of x. And the trick that you use to do that is when you set up your definition of your recursive function, you actually explicitly make the things that you're building functions of x. So p0 of x is 1, p1 of x is equal to x. And then for the remaining values, what we're going to do is we're going to use this relation right here. And I don't want you to get confused that this is different than this. All I've done to get from this relation to this function is shifted the index of n by 1, and then I divided both sides by 1 over n. So it's the same relation, but converted so that a computer can handle it. So let's actually take a look at some of the values that this thing might spit out. Well, what is p, say, 2 of x? That's a good thing to look at. And I happen to know that that is the second Legendre polynomial. Okay, you can go look that up in a table if you like. And we could look at p3 of x. Okay. Now, one property that Legendre polynomials are supposed to have is that when you integrate them in product, that you get 0 out as long as the Legendre polynomials are different from each other. So let's integrate let's see, the product of, I don't know, p2 of x and p3 of x. And then the interval that we're going to integrate on is any symmetric interval, but let's just do from -1 to 1. And we get 0. That's perfect. That's exactly what we're supposed to get. And notice that even though we defined it with this recursive relation, we're getting actual functions of x out that we can work with calculus ideas. So these are functions. If you're not convinced, we could plot them. So let's plot p4 of x. From x goes from -1 to 1. Right? That's exactly what we'd expect to see. In fact, one trick that you can use here is we could show lots of them at the same time if we showed a table. There's a cute trick. Show a table of plots where we're going to plot them all on top of each other. That's why we're using a show command here. And let's make this an n. And then maybe we will evaluate our table from, I don't know, n goes from 1 to 5. Let's look at the first 5 Legendre polynomials plotted together. Well, that looks great, but not very satisfactory because they're all the same color and that's kind of jumbled. So what I could do is, and we've used this trick before as well, we can actually just make sure that each individual plot has a different color by using some kind of command that looks like this. And now we're going to get a family where each member of the family has its own color. Okay, so the whole point of this exercise is to show you that when we're working with these recursively generated functions, they are actually just functions. And that you might have to do a little work on the relation to make sure that you get the right kind of equation for relating these things. But once you have it, you just have functions, families of functions. In fact, there's an entire theory of using these functions to do approximation that shows up in linear analysis that I think would be very appropriate to approach with Mathematica or MATLAB, where you could actually see how these things work and why they're useful. So that's the basics of recursion. We talked about doing recursion to generate sequences of numbers. We talked about doing recursion to generate sequences of functions, different ways that we can make sure that we have functions versus numbers. We've shown how we can manipulate the output of these things. And we've also shown, even though it's not called this in the book, this idea of memoization, which means that you save the evaluations that you've already made so that you can call on those evaluations in the future. And that's, again, everything that we've written down recursively. We have made sure that we've specified that we want our function to be not just an evaluation, but the assignment of that evaluation to the correct name so it can be recalled in the future. All right, so get started early on this one because the content this week is small. The idea of a recursive function is very easy to explain, but the problems associated with it can be kind of challenging. So get started, and I'll see you guys in Slack. Take care.